Hi everyone, in the last video we were looking at a number of conjugate acid-base pairs, and we made the observation that it really depends on which two things you put together in order to decide when something is an acid and when it is a base. And so you may have observed that in some instances water was serving as an acid, in some cases it was serving as a base. And so because of that, if you just have water all by itself, there is going to be some amount of water that becomes acidic and some amount that becomes basic. Because we have this molecule, H2O, which has lone pairs of electrons, and it has these protons that are on there, we have this partially negative side, and we have this partially positive side. It's that partially positive acidic proton that is able to leave, and it's this partially negative side that has the lone pairs on it, which is able to accept a proton. So what happens here is that the acidic one, just the one that we have named to be the acid here, is going to have this proton leave because this lone pair of electrons is going to grab that proton. So the base is able to accept a proton. It's doing that on its partially negatively charged side, and so it's going to grab that proton. So ultimately, what are you left with? This acid over here that is willing to give up a proton is going to become an OH, right? It is going to become that conjugate base. When we have this base over here on the left side, this water molecule, this is the one that's going to accept, so that starts off as a base, and it's going to become its own conjugate acid, right? So it's just like we were looking at before with these acid-base conjugate pairs, but now it's just water all by itself. And so the fact that water by itself can automatically become ions, either hydronium ions, H3O pluses, or OH minuses, hydroxide ions, we call that autoionization, and that's because we automatically become an ion. So because water has this ability to just automatically ionize into the component ions, hydronium and hydroxide ions, we can describe this as an equilibrium reaction, right? Where one molecule or 1 mole of water and another 1 molecule or 1 mole of water are going to spontaneously, a small percentage of them, form H3O pluses and OH minuses, right? This is saying it's a reversible reaction, so everything we've already learned about equilibriums applies, and we also remember that in these equilibrium reactions, when we were talking about acids and bases, it usually means that the weak forms don't proceed very much in the forward direction. It's actually kind of that reverse direction that's more important, right? So only a very small percentage of all the water molecules are going to turn into these ions in this reaction. So if we can do everything we know about equilibrium reactions, then we can go ahead and set up what the equilibrium expression for this would be, right? So equilibrium K is going to be products over reactants. Things that we have to remember when we're doing this is that we're talking about concentrations. We are also talking about only aqueous and only gas phase. We are going to forget about the liquids and we're going to forget about solids. So in our instance here, what we're talking about is products, H3O plus, some concentration of that, times the concentration of OH minuses over the reactants. Well, the reactants here are liquids, so we're going to put a 1 there, not a 0, but a 1. And so this is really just going to simplify to H3O plus concentration times the concentration of OH minus. So this is a very specific K, equilibrium constant. It's the K of water, and so we're just going to call that K sub W. And so this is the same thing that is written over here in the text for you. So at 25 degrees Celsius, Kw has been determined to be 1.00 times 10 to the minus 14. And so this is going to be temperature specific for this equilibrium constant. So in order for us to determine what is the concentration of H3O plus and OH at equilibrium, we can use an ice table to figure that out. Great. So when we do our ice tables, the things we want to do to set this up, we definitely want to do ice, initial, change, equilibrium. We want to make sure we have the nice balanced chemical equation at the top. If we have a K, our K is going to be related to equilibrium. If we have some initial, then we might have a Q, right? So that would be up there. So in order for us to do this, what we're going to want to do is remember nothing is going to go in this column or this column because those are liquids. All we're saying is that initially we have 0 of each one of those ions, right? Initially, unless otherwise instructed, we're going to say that we have no products formed. Now, we are going to change between the initial phase and the equilibrium phase, and we're going to produce H3O plus and OH minus. So we are going to add an X in both of these cases, right? The molar quantities are 1 and 1 in those products, so we really have a plus 1x and a plus 1x, and we typically don't write those 1s, so we're just calling that plus x and plus x. Now 0 plus x at equilibrium is just going to give us x. 0 plus x at equilibrium is just going to give us x. And so now we have the ability to solve for x because we already know what our k is. We have a value for kW, but we also can write the equilibrium expression, and we did that on the previous slides. So now what we have is the opportunity to substitute in the x and x into the places where our concentrations go for the respective ions. So now we're saying that 1.00 times 10 to the minus 14 is going to be equal to x times x. That's going to be x squared, so we can just take the square root of both of these sides, and our calculator is going to tell us that what we have for x is going to be equal to, our calculator is saying 1.00 times 10 to the minus 7 when we take the square root. So that's x. So now what we need to do is we need to make sure that we put x back into our table in the appropriate places. So that means that the H3O plus concentration at equilibrium is going to be 1.00 times 10 to the minus 7, and then the same thing here for the OH, 1.00 times 10 to the minus 7. So if the question is asking us what is the hydronium ion concentration at equilibrium, then we've got it. If they're asking us what is the hydroxide concentration at equilibrium, we have that number as well. And so this is it worked out for you in more of a typed out version, but it's what we just did on the previous slide. So in example 2 now, they want us to do the ion product of water. They want us to get another kW. This time they've changed the temperature and they've changed the value. So at a different temperature, we're actually going to get a different kW value. So if we did that with an ice table last time, then we should consider doing that with an ice table next time. So we've already set that up for you. We're keeping in mind this is going to be for a reaction occurring at 80 degrees Celsius. We still have 2 liquid water molecules. They're going to come together to react. We're going to end up with some H3O and some OH. The liquids do not become part of our ice table, so we're not planning on putting anything there. We're still going to do that same thing where initially we're going to have 0 of each of these ions as a product. We're going to change, we're going to produce these. And so we're going to have a plus x and a plus x. When we get to equilibrium, it's 0 plus x, or just x. When we get to equilibrium, we have 0 plus x, which is just going to be an x. We have a value for kW. We can also relate that to the equilibrium expression. So that value is going to be equal to the hydronium ion concentration times the hydroxide ion concentration. We can plug in, we can say that it's going to be 2.4 times 10 to the minus 13 x times x. This is going to be an x squared. Let's take the square root of both of these sides, and our calculator is going to tell us what x equals. Our calculator doesn't care about significant figures, so we get a very long string of numbers. We go back to the numbers that they gave us in the problem. We had 2 sig figs here, so we're going to want to have 2 sig figs, and our final answer, that 9, is going to be helping us round up. So our final answer then is going to be x equals 4.9 times 10 to the minus 7. We're going to then want to distribute that into the appropriate places in our ice table. And so now we have added that to the missing spot in our ice table. And if you'd like to see it all typed out, we've also got it typed on the slide for you, probably better and more neatly than my handwriting. Alright, so yet another example. The hydronium ion, so hydronium is going to be our H3O+. They give us that concentration, so the concentration of H3O+ is going to be 1.7 times 10 to the minus 6 molar, right? Because this is going to be a concentration. This is 25 degrees Celsius. What is the concentration of hydroxide ions in the rainwater? So now what we're going to have to do is we're going to have to remember that we can come up with the dissociation constant of water at 25 degrees Celsius. We can plug in the H3O that we have, and then we can calculate the missing part, which is the OH. So let's go ahead and start working that out. So we have the dissociation constant for water at 25 degrees Celsius as 1.00 times 10 to the minus 14. And we can set that equal to the equilibrium expression for that balanced chemical reaction equation that we previously saw, and now we can plug in the value that we have and solve for the value that we're missing. So hopefully you see now that we have 2 numbers and just 1 variable, and so we can divide each side by 1.7 times 10 to the minus 6 to get the OH concentration by itself. So when we do that division, we get OH minus by itself. That's going to give us something on our calculator like 5.88235. Our calculator doesn't care about sig figs. In our original problem, we had 3 sig figs and we had 2 sig figs. This is going to be multiplication and division, so we care about the least number of sig figs. Our final answer needs to have 2 sig figs, with that second 8 telling us that we have to round up. And so our final answer here is going to be 5.9 times 10 to the minus 9 molar. And so if you'd like to see what that looks like in a typed out form, we've done it here again for you. And so that's going to be the end of the slides for this section, where we're interested in autoionization and how to calculate hydroxide and hydronium ions based on that equilibrium expression for the dissociation of water. You can go ahead and close this one and move on to the next.